So I love this next section because it just really makes you think about what you're really doing when you find gradient vectors and directional derivatives, but in the context of a contour plot. No context, we're not interpreting anything. It's more of an exercise of just thinking about these concepts. So remember, the gradient vector, come on, pen. The gradient vector is defined to be the partial derivative with respect to x at the point of question, in this case 2, 1, in the I direction, plus the partial derivative with respect to y in the j direction. Now in this case, because I'm going to be estimating these partial derivatives from a contour plot, I like to think of these partial derivatives from the Leibniz point of view. So Gottfried Leibniz would have said, instead of h sub x for the partial derivative with respect to x, he would have said changes in that output quantity h relative to changes in x. And changes in that output quantity h relative to changes in y. Now I like that because it just makes my brain think about what I'm doing. I'm at the point 2, 1. Here I am. And I need to figure out an estimation for changes in h relative only to changes in x. I hope you can see the cursor moving here. So I'm at the point 2, 1. I can't go this way for the partial with respect to x. I can only go this way. And so let's just go. Now I know this is not going to be instantaneous kind of a deal. That's why they say estimate. So I'm just going to go to the next convenient contour, which would take me to there. So here's what I notice. How does h change? H changes, now remember I'm going this direction, h changes from 16 to 12. So h changes by decreasing by 4 from 16 to 12. That change in h relative to changes in x. How does x change? X changes from 2 to 5. So I would say x increases by 3. So just as an estimation here, changes in h relative to changes in x would be about -4/3, or let's call it -1.3, just since we're estimating anyway. Now, what about changes in h relative to changes in y? So we're at the point 2, 1, and so let's go this way. Let's go to a convenient spot. I don't know. We can go here. So y increases by 4, or I almost said y. The function h increases by 4, 16 to 20. So the change in h would be an increase of 4. And that increase of 4 relative to changes in y is when y changes from 1 to, let's see, these are going in by halves. So it's not even a half. Maybe it's like 0.9. Now it's a decrease though. Notice y decreased from 1 down to like 0.9. So that's a decrease of 0.9. All right, so if we just estimate that, what's 4 divided by 0.9?
It's about 4.4444.
And that's going to be a negative. And so we'll say -4.4 j. So I'm estimating the gradient vector of h at the point 2, 1 in that way. All right, now that we have that, we can get the directional derivative at the point 2, 1 in the direction of the point 4, 0. Remember, the directional derivative in the direction of a unit vector at a point is found by taking the partial derivative with respect to x times the horizontal component, or the I component of that unit vector, plus the partial with respect to y times the j component of that vector, all scalar, dot product scalar. Now, we've already got these two things. We've got hx and h sub y. We've got the partial derivatives. I called it a -1.3, and a negative. It was a negative 4.4. Now I just need a U1, U2. Now we're going at the point 2, 1 again. 2, 1, I'm right there. And I'm going in the direction of the point 4, 0. So we're going that way. So we're following that vector. Let's see, that vector in terms of components, let's label it vector V for now. I'm not going to call it U because U is for unit vector. I don't think that's a unit vector. I don't think that vector is 1 unit long. In fact, I have a hunch I'm going to have to scale it back some amount. So I'm in that same direction, but only 1 unit in length. So my rate of change is per 1 unit of whatever. And so let's see. So 2 to 4. So this is a 2i, and this is a decrease of 1, so it's a minus 1j. I'm calling this vector 2i minus 1j. So the magnitude of that vector is the square root of 2 squared is 4, minus 1 plus 1, to square root of 5. See, it's not a magnitude of 1, it's a magnitude of the square root of 5. And so to make my vector a unit vector, come on mouse, I'll go over here. The unit vector in that direction is going to be 2 over the square root of 5i minus 1 over the square root of 5j. All right, so the u1, 2 over the square root of 5. The u2, 1 over the square root of 5. And let's just, hey, we're estimating, right? These were based on estimates. So we're all estimating. Let's estimate. I'm going to grab the calculator and figure it out. So I jammed it into a calculator. Also, I lost my negative when I brought it over here. And so this thing computes to positive 0.8. And I know if you look at the solutions, I'm looking at it now, they get a 1.6 for the solution, but it's all based on how are you estimating up here. So how do you estimate these partial derivatives? And there's different ways to do that, but 1.6.8, within some margin of error or something, we could say we're in the ballpark. All right, which appears to be the larger value? The partial derivative with respect to I or the partial derivative with respect to j. Now, I think it's funny. Maybe they did this on purpose to make you think. But if you're a here I go, metaphors again. If we're thinking about a partial derivative with respect to I is the unit vector in the direction of x. So this thing right here is really just saying the partial derivative with respect to x by saying you're going in the direction of I. Just an alternative way, equivalent way to say it. So you could think of it as the partial derivative with respect to x versus, and then likewise, j is the unit vector in the y direction. So this is just a partial derivative with respect to y. And the question is just which one appears to be larger in value. At the point 2.5, 1.5. 2.5, 1.5. We're right here. All right, so let's suppose, just to get an estimate here, let's suppose we move in the x direction first. Let's go this way. So in the x direction, if x decreases by 1.5, then the output value increases. So I'm going back to Leibniz. Thank you, Leibniz. I'm going to think df dx. So in my just estimation here, my function increased by 4 units from 12 to 16, while x decreased by 1.5 units. That was an increase and a decrease. So we're going to have an overall negative rate of change for df dx. How about df dy? Same point, 2.5, 1.5. Let's think about y now. Y decreases by, there I go again. The function output decreases by 4. So we're going to have a decrease here, while y increases by 1. Ooh, to call that a little less than 1.5. A little less than 1.5. But still, I lost my symbol there, didn't I? We had a decrease and an increase. We're still going to have a negative. But I guess the question now is, which one of these is more negative and which one is less negative? Because on the number line, if you think about a number line, you have 0 here, you have like -1, you have -2, you have -3, etc. So if I'm looking for the larger in value, I'm looking for the number that's furthest to the right on the number line. The further right you are on the number line, the larger we are in value. So the more negative, the smaller the number, the value. We're just focused on the value here. So let's see. If we just do based on my estimation here. Here I said in the df dx, I said the function output went from 12 to 16. That was an increase of 4 over an x decrease of 1.5. It was a solid 1.5. Now negative 4 divided by 1/2. Here, I said the function output decreased by 4, while x increased by, I claimed it's a less than 1.5. Half, 1. See, I don't get all the way up to here. It's less than 1.5. Let's call it 1.25. So the question would be, which of these two numbers is more negative? -4 divided by a larger number, or -4 divided by a smaller number? Well, wouldn't that one be more negative if you took, let's just do it. -4 divided by 1.25.
It's -3.2.
-4 divided by 1.5.
It's about -2.6666.
So this one is more negative. Well, if it's more negative, -3.2 is like over here. -2.67 is like over here. And so the more negative one would be this one, would be this one. And so the question was, which one was larger in value? Well, the more negative, the smaller in value, the furthest left on the number line. This one is further right on the number line. And so to answer the question, which appears to be larger in value, which one appears to be larger in value, I would say this one appears to be larger in value, less negative.